London. London. Here we go. All right, so London dispersion is weaker due to less mass and less surface to surface contact. All right, so highest freezing point, aka cancel your stuffs in the back. Nay. Go when you finish your multiple choice, bring it to me. You need a pencil. Okay. Highest freezing point means highest. Freezing point is just the opposite of what? Huh? What? Melting point. Sorry, I think you said boiling point. Okay. So highest melting point. Because it's just the opposite. So we say freezing point a lot. It's just like kind of a condition that we talk about more so. So highest melting point would be the one with the highest IMF. Back room. So which of these would have the highest interparticle attractions or intermolecular forces? Yeah.
Acid sodium chloride.
Right. So this one's ionic. The rest of them are covalent. Ionic wins every time. No choice. No question about that one. Highest vapor pressure. Highest vapor pressure means easily vaporizes. I have to write this out to myself so I remember what highest vapor pressure means because it's creating a lot of vapor. Who? Abby. I try to say Aggie and Gabby and Abby at the same time. You should be going across the board going, okay, this one is, what are the four types? Metallic, ionic, covalent, no, we're covalent. This one's metallic, it's mercury, people. Okay, that's metallic, so that's probably out. They don't vaporize, that'd be awful. Titanium is metallic. Water is going to be a covalent compound undergoing what IMF? Hydrogen bonding. This is a covalent compound undergoing London dispersion. Okay. So London dispersion, and this one is going to probably be octane. Yeah, octane here. Because it's going to have the weakest attractions for one another, but we'd actually need to know a little bit more information because sometimes if you have a severely massive structure that's covalently bound, not network covalent, not that big, but I mean that's pretty large, its London dispersion can actually outweigh hydrogen bonding of this little bitty water. So we had a problem like that on 2 years ago AP exam. Everybody freaked out.
What is the term for like really big covalent?
I say 50 plus.
Like C50?
Buckyballs. Okay, lowest melting point, aka weakest attraction, so it's going to melt really, it's going to be the first to melt. Who's the first to melt? Shout it out. Why N2?
Non-polar.
Right, so it's covalent. So then our problem is like, okay, we got, covalence, that's the only one that's ionic, that one's out. But then you have to figure out the weakest interaction of those covalent. So that's nonpolar. This one, you're drawing in your head what's between the Z and the O. Pretty sure it's triple bond. But regardless, we have a dipole moment, right? So that's definitely polar, and this one's definitely non-polar. So then we have two contenders, non-polar. So both of these are undergoing London dispersion and London dispersion. This one's dipole. That's strong, right? So then your last and final choice comes down to what?
Greater mass.
Greater mass. So the greater mass is going to have the stronger 44 grams per mole, 28 grams per mole. That's going to have the stronger London dispersion forces between one another. This one's have a weaker London dispersion force amongst another. So that should be the lowest melting point. Strongest hydrogen bonds, Gabby.
H2O.
What did you say? H2O. Okay. So this one has a large electronegativity difference, as does this one. All of them have a large electronegativity difference, right? Hydrofluoric acid, H2O with the O and the H and the N and the H right here. So they all have a large electronegativity difference. Some of them are bigger than others, yes. But this one has, it's weird, this one actually has 3 lone pairs on it. This one has 2. But water is always larger. It's always one of the largest strengths in terms of hydrogen bonding, so we tend to choose that one over any of the other forms of bond. Okay. Highest, smallest heat of vaporization. What does that mean to you? Right, you look at it, it vaporizes, right? It takes very little energy to vaporize. Heat of vaporization, so weak attractions for itself. Who? methane, ethane, or propane, right? So that's propane, so they're all single bonds between there, okay? So methane is definitely because it's got the least surface contact and least London dispersion forces. Largest enthalpy of fusion. So fusion means fusion. So melt, right? So you're taking solid going liquid, you're melting. So who's gonna put up a fight? Okay, so we've got magnesium oxide, we got lithium oxide that should be kind of sticking out to you. This is covalent. These two, how did you choose between the two? Greater what? Charge product. So this is a 2 plus, this is a 2 minus, this is a 1 plus, this is a 2 minus. 2 times 2 is 4 wins. Okay? Especially if you have, I mean, it's easy when you have different charge products. You just figure out who's going to have the largest charge product that's going to have the strongest attraction for one another. But if you have the same charge product, what do you go to? Size, not mass. Generally, yeah, I mean, it kind of works, but larger things versus same-ish size things, larger things are going to have a bigger distance between the nuclei and attractive forces. So this one's easier to break, this one's harder to break. Large things don't stick together very well. Okay, last but not least, lowest vapor pressure. Lowest vapor pressure means what? Doesn't vaporize. Doesn't vaporize means strong attraction for itself. Strong attraction for itself means high intermolecular forces. So strong IMF. Who? Why this one over this one? Okay, this one has what kind of IMF? So I mean circle that. What kind of IMF is here? Dipole. Okay, so this one's got dipole because there's a dipole moment pointing upwards. It's not hydrogen bonding because there's no H bonded to bond, right? So this is going to be hydrogen bound. So it's going to have a lot more. It's got two things going on here, okay? It's actually got hydrogen bonding on one end, and then it can attract with other straight chain alkanes, like alkanes need a bunch of carbons together, by London dispersion. So on the larger the molecule, the more likely it is to actually have two different types of IMFs, right? You can interact with one thing on one end and interact with another way on another end. Cool? Good review? All right, so thank you for watching this video. Friday was a mess, but we got it done, okay? So, I wanted to go, I'll do 9 the other ones later. Check these for yourself. I'm gonna scroll down. These are this is a B through D. Tell me when to scroll. I try to give myself explanations. I'm going to scroll down to 4. Like that. Ask me questions. Can I scroll down to 8? Yay.
Yeah.
Basically, you need to know all the properties of every type of solid. But it's not too bad. I mean, a lot of it is review. So that's why I'm applying for this spreadsheet this week, because nobody got time for this. We have a lot more on IMFs to kind of do the last final stomp on IMFs to get the ground in. Yeah.
For number 6, oh, sorry, never mind. Okay, so for number 6, that that's hanging off for number 7.
This is number 7.
Yeah, I know, I realized that. But it doesn't show it on your paper, so I thought it was another one, and it took me 20 minutes. I was like, oh, what is just O?
Yeah, I'm sorry. I can't do a double bond up on Word. Don't know how to do that. I can take a text box and turn it, but yet again, I know we got time for that. So sorry about that. I should have put it on the board. That's why I usually do these in class with you guys, but you guys were working the whole time, so I didn't want to bother you. All right, and I've got the part D at the very bottom. Yeah. Okay. Because water has two places. We'll sit in that one kind of. Generally, water is the weird one. It usually has more than what it should. I mean, have more hydrogen bonding available than it should. But because water orients itself in such a way, it actually can get closer to each other. This methane this methyl group on the end does not allow for methanol to get as close to to another methanol. So it's got actually weaker hydrogen bonds than water does. So the proximity, the distance between them does matter with IMOs. So the heart makes the distance makes the heart go stronger except for IMOs. Okay. Okay, so this last one. So I want to talk about these. The 4.1 question one. Oh, melts below 100, you already know it's covalent. Okay. But what kind of covalent? You have to hear a little bit more. Insoluble in water. So is it a molecule that's polar or nonpolar? It's insoluble in water, it's nonpolar. So it's not only a covalent or molecular solid, it's a nonpolar molecular solid. It goes a little bit more, it goes a little deeper. 2, conducts electricity only when melted. Only when melted means solid state, nothing's going to happen. So that's ionic. So the ionics have a static electron location, not delocalized. So if it's static, it does not collect or conduct electricity. But once you put in aqueous solution or you melt it to molten state, then it will. 2, 3, insoluble but conduct. So insoluble in water means you're kind of narrowing it down. There's a couple things that can do that, but conductive doesn't say when, so I'm assuming always. Always conductive is metallic. Insoluble in water melts above 500, so it's crazy high, right? So it's probably going to be network covalent. So that should be one of the first things you think about. But then it says does not conduct electricity. Some of them do, actually. Which ones of all your network covalents, which ones conduct electricity? Was that in your videos or am I going over that today? I might be going over that today. Okay, we'll go over that today. I can't remember what you guys done in your videos now. 5, non-conductive in solid or liquid, but does dissolve in water. So you know it can't be ionic or soluble in water. Can be a polar covalent compound, not metallic and not network covalent. So it kind of narrows it down there. 6, melts above 100, so high-ish melting point, so it's ionic or network covalent, but dissolves in water is definitely ionic. So you have a lot of kind of it's like a flow map you go through in your head to get these. Cool? Okay, I'll do the FRQs later, so I want to see those from you before I go over these. Oh, down here. What are at the lattice points? You guys did reading guide 3, I think, for the solids, liquids, or solid corner compounds. So here, what are the lattice points, meaning the corners of the cubic structure? What's at the lattice point of an atomic solid? Atom. So give me an example of an atom for an atomic solid. Anybody? Anybody? Diatomic, that would be molecular. Diatomic is a molecule, right? So go back. Huh? Carbon? Carbon could be. So you could say atomic solid could be carbon, like graphite or something like that. So I can go with that. Carbon, what else?
Silicon.
Silicon would be like a network covalent. That would be a network solid, actually. It's just weird because silicon is your one big exception. It's usually, you see silicon, usually it's a network covalent. So carbon, beryllium, boron, yeah, that's good. Okay, because once we get past that, they're all diatomic from there, so you can't call those atoms, they're molecules. All right, so metallic solids. Everybody should know. Tell me what's at the lattices. Huh? Cation. Okay, so the cation of the metal after it's lost its electrons to kind of the sea of delocalized electrons. Here. Oh, nope, that doesn't work that way. Okay, so that's like carbon, silicon. Silicon can work, actually. I lied to you, but I prefer that one to go with. Abby, I prefer that to go with network. Okay. Metals with the cation at the corners, delocalized electrons are surrounding it. delocalized electrons are nice because that's allowing for 100% always conductive, doesn't matter what state it's in. The whole non-directional covalent bonding, ignore that really. It just means that there's, you know, a cation here, cation here, cation here. There's different not between the cations, there's electrons around here. They have lots of directions in which the attractions can occur to all the electrons that surrounding them. So it's not unidirectional, it's non-directional. Network solids, we just said silicon. Anything else? Carbon sometimes can be part of the network. So carbon and silicon, they're right below or next to each other on the periodic table. They take on very, very similar properties. It's just silicon has a little different molecular orbital diagram than carbon does because they have more p electrons. So they have a bit different abilities. So these are going to form large, giant molecules or networks. Networks are going to have lots and lots and lots of connections, like AT&T, Verizon, except for in my room. All right, so this is just some quick feedback on some of these solids you guys went through. They do have more directional attractions or direction bonds because they do have a structure that will be repeating itself over and over and over and over again. Group 8A solids. I wonder what is at those points. Something like what? Like any group A, 8A, so helium, neon, etc. You've probably heard of, maybe, I don't know, you ever heard of liquid helium? Liquid helium, it's a coolant?
Yeah.
Okay, so liquid nitrogen is definitely coolant, but liquid helium is as well, but sometimes you can get it down to solids. Okay, so I'm going to scroll down here. I don't think I want to show you this right now. Some of the stuff is from our curriculum, and they changed it last year to be a bit more specific, so I want to go over those specifics, because that, to me, that means it's going to be on our test this year. So I'll go over that when we get there. Right, so you'll be writing some today. You won't be writing a lot, because I think that there'll be quite a bit of review from 1, honor chem, 2, the reading, 3, some of the notes, and we just need to kind of connect some of the dots, because it's very qualitative this time, so that I want you to be able to kind of itemize these things and categorize them in your head. So listen, write, do what you got to do, but I'm going to go through some of these, because after this we're going to do phase diagrams. All right, so bonding, we went over ionic pretty extensively. We went over covalent, a lot. We drew every single type of molecule you could ever draw with covalent. Metallic, really simple. It's a bunch of cations hanging out together. The cations have lost a lot of electrons. The electrons don't go anywhere. They stay in that general area, but they're not going to be in one specific location, because the electrons can kind of hang out and flow around the big cation family around here. So they're called delocalized because they're not in one location. The only difference is if we have to tell the strength differences between metallic bonds, the more, so if you don't write anything, write this, okay? The more valence electrons donated to the C of delocalized electrons, the stronger the bond. Basically, that's just because the cations have stronger or higher magnitude charges. Anytime you have a higher magnitude charge, it's going to have a stronger attraction for some other thing of the opposite charge. So it's basically saying lithium forms a 1+ charge, calcium forms a 2+ charge, and aluminum forms a 3+ charge. Aluminum's melting point, or any of those physical properties you guys learned about, it's going to be higher and more, it's just going to be higher magnitude due to purely to the fact that aluminum is 3+ charge and it's more strongly attracted to any of its electrons or counterparts. Cool? Alright, do you guys some more a second? Alright, so with metals and metals can come together. Multiple metal types can come together. What do they form? Alloys, right. Alloys are just physical mixture of metals, but they do take on different properties, okay? Alloys, for some reason, they have really upped the ante on understanding a lot about alloys, so we have to learn about 2 types of alloys, okay? Substitutional and interstitial. Substitutional is going to be basically something is substituted. They were really creative with that name, okay? Substitutional. So that one's easy. Basically, the metal that they're substituting, because it's metals, or alloys are just metals and metals. The structure shape will stay the same, body-centered, face-centered, stuff like that. I'm not going to go into extreme detail with that. We used to have to calculate the atomic radius or diameter by doing the Pythagorean theorem. That was so much fun. They took it over our curriculum, so I don't teach anymore. But I couldn't remember the Pythagorean theorem for the longest time.
Are you seriously?
I'm serious. Like that's my favorite. I will do one for you. Not right now. But I love calculating the atomic radius. It's like I feel super duper smart when I do this. Because you get down dirty with the cubic centered, and yeah, it's cool. Okay, so the body centered or face centered or cubic centered, whatever the shape, the general unit cell shape is going to stay the same, except you're substituting in a pretty much the same size, same-ish radius for another metal. So commonly you'll see zinc and copper because they're right next to each other on the periodic table, right? I mean, they're literally right next to each other. Atomic radius does not change by maybe one or 2 picometers. Doesn't change very much. So zinc will pop in for copper. Why? Because copper is expensive. Okay, it's expensive. So that's why we no longer have a lot of copper or pennies, because they try to phase those out because the penny was worth more than a penny. So they're losing money. Because people would just melt it down and be like, hey, I've got some copper for sale. Would you like some? Okay. So they do that because of purely the ability to do that based on size. Now it does change the property of it some, because zinc has different properties than copper. Okay, we'll get into that in a second. Interstitial. Who's ever heard of interstitial fluid? Okay, the fluid between cells. Cells like in your body, right? There's a little bit of space between atoms. So I'm going to kind of point that out here. The space is like right here. The space between atoms can be filled with other small atoms, okay? And that's going to be things like carbon versus iron. Iron is huge, carbon is really tiny, so it can fit inside the interstices of the metallic lattice. Now metals, I know we don't normally say they form lattices. They do. They form a lattice just like this. Okay, they do, because all the cations come together, the electrons are kind of just a big C around them. So they do form a lattice. So this one down here, the interstitial one, and the other one actually, they both change the properties of metals. Metals are generally malleable, ductile, high melting point, conductive. Okay, you maintain the conductivity, you maintain the high melting point. You change the ability to hammer it out into a flat sheet, because what happens is normally you start to hammer something, it starts to become brittle and it starts to break. No, an electron jumps in, stops it from breaking. Another electron comes in, stops it from breaking. And it starts to do that over and over again as you pull it into a wire, flatten it onto a sheet. So if you add a couple different components from the chemical perspective, it actually makes it less malleable and less ductile, because there's not as much space for electrons to move around it. Yeah.
Is this steel still malleable?
Somewhat, it's less, versus, so more rigid, reducing malleability ductility versus the pure metals.
What's stainless?
It's steel with a with a something oxide, iron oxide layer on it. It might not be iron oxide. It's an oxide layer on it. Iron oxide is rust, but it can take on a different composite, if the lattice is shaped is in a specific arrangement, it will put off a different view. Yeah, I guess I was going to say tint, but view. It just depends on how the light's reflected back. Okay, so it might not be iron oxide, it might be another one. Okay, so basically you have to be able to say, based off data, let's say they give you metal 1, metal 2, and metal 3, and they say this one's the highest, this one's the lowest, and this one's the medium. Okay, the medium one is most likely going to be the alloy, because what happens is it's a blend. This may have been the pure metal, like pure copper or something. This may be copper and zinc, and this might just be not zinc. This will be something else, like lithium or something. So they just want you to be able to compare the properties of alloys versus the pure metals and explain why. particulate drawings are going to look something like this. So you can see it's in lattice form. The substitution has occurred, so we've got green and orange versus just orange. This is interstices. Interstitial is between the atoms of a particular metal here. And then this one, you can see the difference in size. It's minimal. So that's a substitutional one versus this one where it's between, you know, the original metal is still there, but you've got interstices. You got some space taken up there. And this is a blend of both. So looking at the pictures, looking at the properties, they want you to be able to compare it to the pure metal. Okay, so well, that's good for alloys for now. Oh, and this is a recap. Did. This one, I didn't go through density. The density of the substitutional one will be like an average of the pure metal, like for example copper, and then the pure metal and its substitute like copper and zinc. And that kind of makes sense because you're literally, it's the density of the two metals and it's an average. It doesn't have to be a direct average, it can be a weighted average, but it's still just the density between the two metal identities. So they might give you just some data and you have to analyze it. And that's what I was talking about, the stainless steel oxide layer can form over the top too, based off of chemical reactions, and it can change up the chemical reactivity of it. So aluminum foil, it's a lie. Aluminum foil is not aluminum foil. Aluminum foil is aluminum oxide with aluminum underneath it. So that you can take a Brillo pad or steel wool, you can scrape off the aluminum oxide layer, and then within nanoseconds it's back, because it immediately reacts with the oxygen in the air and it makes a layer. Okay, so that's like on the All About Owl lab from like the very beginning of time. Yep. That's the density is a little bit off. Was Nick here for that? He's acting like he wasn't here. He was here?
Yeah.
It's like the second day.
All about what?
Owl. My friend Aluminum.
You were here.
For like 3 days.
Pussy play. I don't remember. Okay, well, I'll check your lab number. All right, so non-bonding atomic solids. Okay, so basically, a couple of examples that you need to know for molecular solids: solid xenon, solid argon, solid krypton, maybe. But they have really, really low attractions for one another. But they're huge, right? So their hugeness, their size, means that their electrons can rotate around. What's the word for that? Polarizable. Polarizable, okay. The electrons are polarizable, so they do have London dispersion forces amongst them. So I couldn't remember if I put this on your video, so I haven't checked that yet. But they take on a lattice as well, so most solids do take on a lattice, held together by weak London dispersion. I'll underline the important things. Low melting point, non-conductive. Pretty much the properties of a molecular solid, right? This one just happens to be non-bonding because they're forming a lattice just from their true atoms and not a molecule. I think I kept saying molecular, atomic solids. Molecular solids are just in a second. So I didn't have any dry ice today. We wanted to give blood instead of getting dry ice, you know. The lesser of the two evils here. So the better of the two evils. No negative, so you know I gotta give back. So a couple of the molecular solids you're probably aware of are carbon dioxide, solid, dry ice. These are allotropes, sulfur and phosphorus. They're allotropes. That's naturally how sulfur exists. It's a really pretty yellow solid, but they're molecular solids or atomic solids. Sometimes we interchange those, but this one's definitely a molecular solid because that's a molecule. This one is a molecular solid because it's not just a single atom, but it is all of the same atom. You see the difference? Most time molecular solids are true molecules of different atoms, but these happen to be allotropes, which are molecules because they're not single atoms. They're a bunch of the same atom together. Okay, so their forces of attraction are also usually very low. Usually they're going to be nonpolar, so they're going to have low melting points, non-conductive, because most of the time they're nonpolar molecules embedded in that solid form. You can see, so these come off with very different properties based on what they're made of, but dry ice is actually one that is a very, 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 very low melting point. It actually is, it's at a different pressure, not 1 atmosphere, not normal pressure will it melt. It actually goes straight to sublimation and goes from solid to gas at 1 atmosphere pressure. It's got a really low melting point. Review so far, kind of ish. Okay. Okay, networks. Networks are going to be large, giant molecules. So these giant molecules, these are the coolest ones ever. I have some great pictures for you. Oops, as I kill my glasses. Okay. I'll be quiet and let you guys write down some of these first. Read and write what you want, and I'll explain some. Give me about 8 more slides and I'll give you a break. Yeah. It's not 666. Four is the magic number because it can go in X, Y, Z, and other axes. It's actually in the same plane. They're same plane, it's just different axes. Okay, so network covalent solids. They're all covalently bound, so they're sharing the electrons, but they're a large network, like maybe hundreds to millions of bonds between these things. So hundreds to millions of atoms are embedded here. So it's not the fact, it's not just like, you know, eventually we're gonna say these have really, really, really high melting points and boiling points. We're going to say that. But why? It's not because it's covalent. It's because there's a ton of them. Like, geez Louise, it's going to take forever to break all those things. So it's going to have a ton of energy required to break every single bond, like the bond dissociation energy times 1,000,000, okay? So we have a lot of things going on here. Allotropes are considered molecular solids, but if you get an allotrope that's got 50 plus atoms of it in there, then it might be considered a network covalent, because though it may not be covalently bound, we still sometimes like to call them giant molecules and classify them as this. So what you'll see the most in network covalents are carbon and silicon. Okay, pretty much if you ever see silicon, it is part of the network covalent group because it forms great, great, great bonds, and it'll do it over and over and over and over and over again. So it's going to form, usually we have 4 electrons going on, so usually we form 4 bonds, because that's going to allow us to build up a larger structure if we have bonds going in, you know, northwest, south, and east directions. Carbon can do it as well. Carbon has a couple of allotropes you absolutely have to know. They're diamond, graphite, buckyballs. Those are the 3 or 4-ish most popular, most common ones. Not popular, they might be popular, I don't know who they are. So they're most common examples. I can scroll back up.
What's a parking ball?
I'll show you. It's that I have one back there. Those magnetic ones.
Yeah, the little magnetic balls.
You're not supposed to eat them.
I think my friend swallowed one once.
Yeah. Your buckyballs are magnetic, and anyway, you can play with them and build structures. But in Japan, maybe that was U.S. I think a couple years ago they banned them here. You could only buy them from like Japan because they were poisoning children.
Why were children putting them in their mouth?
Children put everything in their mouths. Why do they pick up gum with the powder? Because it's leaking different metals. Because they're not only made of carbon. Buckyballs, like for real buckyballs, they're nanoscale. Like you can't see them. Buckyballs was a toy that they modeled after the atomic level of buckyballs.
So this is
They're metals. It's toxic now.
Can't put it back into another iron cube anymore.
Not iron, probably like arsenic or something like that. Something worse. I have a model of one. Nick, you're so smart, but not smart. Oh, okay. Carbon. Carbon, diamond, graphite, buckyballs, nanotubes. This is the big hot new thing, okay? Who's heard of carbon fiber? Who's heard of carbon fiber? Okay, carbon fiber is graphite, graphene, It's a small, thin layer. They're also called fullerenes. They're used a lot in medicine. They're used a lot in manufacturing. They're extremely lightweight, 10 times stronger than steel. Okay, steel is old school, new school. Nanotechnology is the way to go. So if you're going to go someplace big with science, nanotechnology, they will need you forever. Okay, so let's get into some more details about these allotropes. Diamonds, and then graphite, and then buckyballs. And let me retrieve my nanoscale buckyballs. And my diamond.
Please don't fall.
That's not what I wanted to do.
Sorry, there's glitter on you. It does. You can get it off with baby oil.
Yeah.
We did a Mythbusters experiment. Do you remember that? Maybe that wasn't last year. They figured out the best way to get glitter off. Very functional Mythbusters. Actually was. Okay, so diamond is just a bunch of carbons together. Carbons together occur with an atom. I'm kind of draw on top of this. Sorry. This is coming out. This is going back. Okay. This happens over and over again. So this central carbon here has a tetrahedral arrangement. What's its hybridization? It's got 4 electron domains. sp3 hybridized, right? So sp3 hybridized, but that's going to happen over and 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 over again. Okay. So it's going to happen, a couple million times hopefully to make a big diamond, but if it's a couple thousand times, it'll be a small diamond, right? Just a different size. But pretty much there's no overlap of any unhybridized p orbitals because there are no unhybridized p orbitals. So they're not conductive. They cannot allow for electricity to flow up and down them. Okay. So the properties that come from that structure are non-conductive, aka they're insulators. Non-conductive, opposite of that, or that also means insulators. They have extremely high melting point simply because, simply because of the network of bonds that would have to be broken to actually take that solid down to liquid form. So everything, all the properties, they all reflect the 3D structure centralized around one of those carbons. And of course there's a bunch of them, so you could talk about any of them. But it's all based off of the 3D Vesper model. So this is just a small section of what that looks like. So this carbon here is sp3, this one's sp3, this one's sp3, every single one of them is sp3. Eventually it has to stop. We don't have like a ginormous diamond. Eventually it does have to stop. But there's a good example of that right there, the glittery one. Next. Perfect. Okay. Graphite is just simply what Grant's putting in his pencil right now. Okay, it's just pencil lead. Graphite has a similar but not exact structure as of that of diamond. It's just sp2 hybridized. So this one looks like a lot to write. So I'm actually going to let you read it first and actually dissect what you need to write for yourself.
Does the weak bonding between layers allow it to treat?
Allows it to, yeah, it's a serves as a lubricant for machines and stuff too. It allows it to be slippery like it is on your paper, and it leaves a streak. Much softer than diamond.
So we could burn it out.
You could, burn it. Conductive, not flammable. What's up?
No, I was wondering if we would burn it.
You'd have to really, it's lower melting point. You can melt it eventually. It's lower than diamond probably, but probably not. Unless you put some accelerant on there, like alcohol. Okay, so we have a different arrangement here. Now my pictures are going to be better, but it's essentially a flat structure of carbons. I'm trying to draw this, it's not going to be great. But they have a leftover p orbital that's never been hybridized. So if that layer and this layer, oh gosh, okay. If they were to interact, they would interact from a p orbital here and a p orbital here. And so those p orbitals can overlap each other, allowing for electrical current to travel up and down through the multi-layered structure, solid structure. It's just basically because it's sp2 hybridized. So the structure does yield its properties. I'm going to scroll down so you can see the better picture here. So this is a big layer of trigonal planar appearances. Here, this looks a little bit better. So it's just a flat, it's kind of like just a big bunch of hexagons together, but each of these has a trigonal planar appearance. So there's a p orbital between them, here and here, that allows for electrical conductivity, but is not a true bond, because they're not actually overlapping a ton, so they're not a true bond. So they could like to draw them like this, because it's supposed to show the delocalized p orbitals, which are allowing for the conductivity to occur. So the structure really does control the function or control the properties. So the only other thing I didn't say is, okay, so they're soft because there is that ability. There's no hard, rigid structure like a diamond. They can slide past each other, which can allow for you to write on paper. They also have mainly London forces between them, which is fairly weak, which allows it to slide past each other. They are conductors. We know that from the electrolytic cell lab when we had the graphite pencil leads. They hooked them up to the battery. They did conduct. They have a high melting point. The electricity didn't make the pencil lead so hot that it melted. Okay, I'm not going to probably melt graphite anytime soon. So this is more of a flat structure. So its structure being 2D makes it have this specific properties opposite of that of diamond. Cool. Yes.
So could you like make a diamond from graphite?
If you put it under a lot of pressure, maybe.
I just want
Maybe. Could you?
I mean, actually.
Pressure it, peer pressure. So buckyballs are fullerenes, nanotubules are all kind of in the same category. They're huge. They're like 50 plus carbon atoms, okay? So they have lots of different shapes that they take on. Buckyballs are spherical, like Bucky, my friend Bucky here. Somebody made this last year for me. It's like a soccer ball. So this is C50 it's supposed to be. I'm not counting right now. C50 is buckyballs. Nanotubules, you can assume, has like more of a tube shape to it. And that's what graphene, they use for graphene, which is a structural component to many, for many manufacturing processes. These are some of those properties, and I'll give you a minute to write those down, and then I'll talk about them. And earlier I said 10 times stronger than steel. I'm pretty sure it's 100 times stronger than steel. And that's what they're moving that way. Yeah.
So do you think someone can make a house out of it?
Yeah, probably. If they're making airplanes right now with carbon fiber, which is essentially nanotubules. Airplanes, Corvette car, like the hoods of the Corvette, so little old ladies who get a Corvette can take that roof off so you can have their hair blowing in the wind. What else is being used? They use carbon fiber, which is graphene and nanotubules, in golf club shafts, tennis rackets. They use it in a lot of stuff right now.
They use it for bikes.
Oh yeah, carbon fiber bikes. We are starting to experiment with the benefits to the consumer side of things and seeing if we can outweigh the manufacturing processes, because I'm thinking it's got something to do with the Environmental Protective Agency, EPA, to work with something more carbon-based, which is organic, technically, than heavy metals, because metals are very poisonous to our water systems. Go Earth. Okay, so they are conductive most of the time, which will allow us to have some of that, some of the conductivity we might need in specific things like some manufacturing processes. Low resistance, meaning so they're flexible. They are not going to limit, like there's no Ohm's law going on where they're going to limit the amount of electrical flow through there. They're very, very, very strong though. So I'm pretty sure, I'm thinking it's either a 10 or 100 times stronger than steel. I can double check that. But one of the coolest things, this is a medicinal application. They're free radical scavengers. We heard about the free radicals already. We heard they oxidize our cells. Pretty much oxidation of your cells is what causes you to age. Okay, so if you can stop oxidation of your cells, you could be young forever. Okay, there's also the telomeres, which are, your chromosome looks like this. Telomeres at the bottom, they shorten and they eventually start losing code, which would stop allowing for cells to make good cells. They start making bad cells, and then they just kill themselves, apoptosis. So eventually, if we can get free radicals to stop harming our cells, we can increase our longevity of life. So what they'll also do is they do this to stop cancer cells. So cancer cells, they put out these singlet oxygens, which are free radicals. So cancer cells cause other cancer cells to occur because they're peer pressuring them into doing it by pretty much destroying their ability to control their replication and some other things. So if we can put free radical scavengers, which are just essentially big buckyballs, okay, if we can put these big buckyballs into a person, which we can, and we can cause the buckyball to react only under specific conditions, like, for example, a specific wavelength of light, we can make it capture, the free radicals, or capture the oxygen that's put off by the cancer cells and pretty much stop the disease. They're doing this right now at UNC Charlotte with one of the guys I'm working with this summer. So they're putting the these are like big, they're called electron sinks, because they actually capture electrons as well. And so they're putting them in people's bodies, and they're taking, it's called photodynamic therapy. Photo means what? Light. Dynamic means changing light. So photodynamic therapy, they'll shine a little laser at some person's pretty superficial cancerous area, and they'll shine a laser there with a specific wavelength of light. They'll activate the buckyballs will capture the similar oxygens or whatever the cancer cells are putting out, and it'll treat the cancer. Yeah, they've had success.
So, at that point, would it not be poisonous?
The buckyball's never poisonous. The buckyball, carbon buckyball, the toy buckyball that little boys bought and ate are poisonous. Buckyball has no metal in it. That's straight up carbon. Buckyball toy has metal in it because they're magnetic. Carbon's not magnetic. Okay, so, I said carbon 50, that's carbon 60. That's carbon 60, my bad. So don't worry about anything else I just told you about the rest of the delivery of buckyballs for medical treatment. My sister actually worked with that a lot in NC State, so they have it everywhere. All right, now we're covalent again. So now we've kind of just covered the carbon side of things. Let's do the silicon side of things. So silicon are called, anything with silicon in it is sometimes called a silicate. Silicate, the best example of a network covalent with silicon in it is sand. That's it. Silicon dioxide is just sand, quartz, rocks, beaches, spring break. Okay? So that's all it is. It takes on the tetrahedral structure, just like carbon did. It has, I have a picture down here that's going to be better, but it's got 4 little legs. Oops. And it kind of just butts up against another silicon dioxide, and they kind of share the same oxygen. So I'm trying to show you, this is one silicon dioxide, and this is another one. The silicon's in group 4, so it also likes 4 bonds, so it's going to do that over and over again and keep sharing with all the other silicon dioxides. So they have that network formation after they've done that multiple times. This can also be treated, so silicon dioxide can be treated to form something amorphous. Amorphous means doesn't have a shape, like glass. You know, glass is just sand. Yeah, okay. We've all seen, what's the movie with lightning strikes? What is Sweet Home Alabama? Thank you. We've all seen it.
No.
We've all seen it? Oh my gosh.
Oh my god!
Sweet Home Alabama. Lightning strikes the sand, makes a big glass pool. What do they do with
They
it?
sell it. They're
They cool it and sell it?
Yeah, they make designs.
Yeah, I can't remember what they sell though. Okay, we'll have to watch the movie for the chemistry behind it. Okay, so if you can make the amorphous solid, we call that glass. You can also add additives to it to make it colorful, mercury, cobalt, you can add all kinds of additives. If you have quartz, like rose quartz, yellow, kind of a yellowish quartz, it's just a bunch of different elements that came in there that are actually impurities, and impurities make it that color, which most people don't consider it an impurity or a bad thing anymore because it makes a different color. So if you can make a homogeneous solution, homogeneous means the same throughout, same structure throughout. So that's going to be more of what we call the crystal, whereas amorphous solids are going to be more like glass. You can't. I don't have a picture of glass up here. I don't think I do. Nick, what's up?
You know, pour lava on ice, it's like glass. It's really cool.
Lava on ice?
It's like glass.
I wonder if it's because of the silicon. I wonder if there's silicon in magma. What's in lava? What makes up lava, people? I mean, but what is lava made of? Egg face what?
Really super hot.
Rocks are made of silicates, right? What?
Side note, is it just your accent or is it supposed to be pronounced silicon?
Silicon?
Yeah.
What am I saying?
So you're saying silicon, but
It's
I
silicon.
said
Silicon?
Or silicone.
Silicon are what they use for breast implants.
That was silicone.
Silicone. Silicon. I don't say silicon. Silicon. Silicon.
So it's just your accent.
Silicon.
Okay.
I don't think it's silicone. It's not silicone because that's what I had to tell my honors chem kids. Was if you people just keep calling it silicone, where am I from? Silicon. Silicon. Okay. What am I looking for? Lava. Lava. Chemical. What's it made of, though, people?
Is made of the
All of the uniform
Volcano world. Oxygen, aluminum, sodium, potassium. So where's we got silicon right there. There we go. Like 27%. Okay. Yep. All right. So, and this was funny to me. Silicon is the geologist. What carbon is the biologist? Ah. Yeah. I thought it was funny. Okay. Okay. This is the most important part of silicon. Okay. We have to know that it's commonly used in. It's a semiconductor. Okay. So it's right on that metalloid line. So Allison point. Metalloid line. Stepping stone from aluminum down on top. Sorry, boron down. Okay. So there's a little stair step. Silicon is a semiconductor. It means it's got properties of both. It's a metalloid. It's got properties of both metals and non-metals, okay? The semiconducting nature of it, people take advantage of all the time. You are right now, if you have your cell phone on, okay? Or you will later today. So it's used as a component to microchips. Semiconductor. You have to know that this silicon is in semiconductors. I'll let you write over here.
Wait, I didn't get the picture.
Silicon's for geologists, because that's like the massive, most important element type in the world of land and oceans and geology.
It's not really that fun.
I didn't know that.
You have to get over it. Sometimes my jokes are funny, sometimes they're not. We have to just deal with it. Okay, so like I was saying, I said this earlier, but silicon has it's in the same group, but it has a different molecular orbital arrangement of its electrons, which gives it that metalloid ability. And that metalloid ability gives it the semiconductor ability. So semiconductor means a conductor under certain conditions. Okay, so this is going to be super, 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 super important for the next slide, because we have to be able to talk about how to change up the conductivity of semiconductors. Okay, so I don't think there's anything else here. Oh, I mean, I think that makes sense. Increasing the temperature increases the conductivity because the electrons are able to be a little bit more mobile because they have more kinetic energy and they're bouncing around like crazy, right? So more kinetic energy increases the movement or the mobility of electrons. So that's the only other thing. And then I have these lovely blurry pictures for you, but they started to actually, you can paint on semiconducting paint, which is actually really cool. Yeah.
When are we getting that break you mentioned earlier?
I got 2 more slides. Give me 2 more slides.
Okay.
I'm so sorry. I'm sorry. I need to talk. Okay. I told you this is after the break. Okay. I mean, this is before the break. Huh?
What did you say?
He's like, bring him to rub.
Okay. Doping. Yeah. This is doping. We dope the chemicals with other chemicals.
It's so dope.
So, doping is something you have to know how to dope the chemicals. It's just impurities. That's all it is. So silicon is on what's flanking left and right. I'm going to explain the purple parts first. Okay, what's on left and right from the periodic table of silicon? Okay, aluminum and phosphorus. So aluminum has 3 valence electrons. Silicon has 4. Phosphorus has 5 valence electrons. Electrons create electricity. They bounce around. So if you've got one less valence electron, aka aluminum, or germanium, no, not germanium, gallium, okay, if you got one less valence electron than silicon, you kind of hold a more positive vibe because you're one less. If you have one more valence electron than silicon, you have a more negative vibe about it because you got one more negative electron, okay? So I'm gonna explain this down here first. If you choose to have silicon, you're making a semiconductor, you're making a big silicon wafer like this one right here. This is a silicon wafer. They make these in like football sizes, like football field sizes. And they go through and they just stamp and they take it out and put it in your phone. Stamp, take a little piece out, put it in your phone. It's just that they just get little tiny circuit, I guess, circuits or transistors out of them. This is one silicon crystal. Crazy. No, I can't. I'm still a baby. So I keep it back here in a nice hiding place. Okay, so that right there, you can dope it by adding other types of elements. So if you add an atom from the next group means you've got an extra electron, right? Like phosphorus has an extra electron. Next group is called an N-type doping because it has an extra negative charge. So it causes one extra valence electron, so it has a negative charge. So all the N's go together. Next group, N-type doping, negative charge because it has one extra electron. So that's the easiest way to remember what P-type doping is and N-type doping is. P-type doping is if you have choose an element with one less electron, so one in group 3, A for example, it means you're adding an atom from the previous group. You call that P-type doping because it has a more positive presence about it, okay? It's got a more positive charge due to the fact that there's one less electron. So your best bet is to have silicon with P-type and N-type dope, or dopings, I don't know how to say that, and because that's going to allow for a flow of electrons that's much more readily available than just one or the other. If you can increase the number of electrons that are flowing and the spots in which they want to flow to, then you've got a good conductor. So generally what we call this one less electron thing, it's called a hole. It's missing one electron. It's called a hole. The hole actually does not exist. We call it a hole because we have to visualize it, but it does not exist. There's no hole in this this structure, okay? So what happens is we set up a little transistor or some sort of electrical area, and you can put holes on one side, which are the P-type, okay, because P-type has one less electron, and you can have the electrons, the extra electrons on the other side, which is what type? N-type. The electrons choose to flow to go fill the holes. So they flow across to go fill these holes, and in the middle we can capture that electrical conductivity. It's just the movement of electrons. So that's basically what they do, what they'll do in your phones. And they use silicon, they use germanium. Germanium means gallium, they use aluminum, phosphorus, not arsenic so much, but they use a lot of things right there around silicon. So the junction is going to be best if you have a junction between P-type and N-type, because that's how we get the best flow of electrons. Electrons are essentially just jumping to fill the hole. And so I'm going to show you a picture of that here. I'll scroll back up if needed on the break. Okay, so here's your silicon, here's your hole. This is the free electron. Sometimes these come together. Sometimes that's bad though, because if all the holes are filled and all the electrons that fill the holes, which electrons are flowing? None of them. So we actually don't always want the electron to capture the hole. We want to keep moving the hole to a different location or finding another way to make electrons travel farther. They're called excitons, and we have a guest speaker Friday who'll be talking about that a little bit too. So you can see they just jump, 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 or jump, jump, jump. And so we'd like to try to get a unidirectional because that's how we can capture the flow of electricity. Cool? You guys are master physicists now. Okay, take your break. Give me 4 minutes. I'll see you then. Go get some bathroom and some water. Nick, talkie talkie walkie walkie. Okay. Walkie-talkie. I'm going to, okay, I'm going to show you this. I'm going to show you the picture first. So, how does the whole semiconductor thing work? Basically, we have our molecular orbital theory. Remember the whole bonding, the sigma bonding orbitals, and then we have the anti-bonding orbitals with a little star on it? Remember that? Okay, so we had, like, our electrons going from, 1s2 or something over here, and 1s2, or 1s2 and 1s2, we put them down in a lower band and then upper band. This was the bonding orbital down here, and these are the anti-bonding up here. That's basically how a semiconductor works. So what we have is, as you go up in the as you increase the electrons in the periodic tables, the distance between the bands, between the bonding orbitals and the anti-bonding orbitals, they differ. Okay, so if they differ, that means we've got some problems in conductivity, okay? So this is called the bottom one, the valence band, is called the kind of the bonding orbital, and the conduction band is called the anti-bonding orbitals, and that's basically where we put those orbitals in the molecular orbital diagram. So if you have a small energy gap between, or just a small gap in energy between the bonding orbitals and the anti-bonding orbitals, that's a semiconductor. If you have a very large gap, that means there's no ability for the electrons to get excited. So remember, electrons can always get excited, oops, that's an electron, and they can move up to an upper level, and they can fall back down. If they fall back down with a specific amount of energy, it can create light. Well, this is a little different. It doesn't create light. It creates electricity, just releasing mobile electrons. So if we have a large gap, there's no way this electron down here can jump up here and then fall back down. It's too big of a gap. So it's called an insulator because it's just not going to have mobile electrons. Not very many, right? Small gap between the energy levels means that it's a semiconductor because the electrons can jump up and then fall back down. And if they're literally touching, if the gap's so small, we just call it a conductor because there's essentially there's no hindering this electron from moving up and then back down, and then up and then back down. So the bigger the energy gap between the bonding orbital and the anti-bonding orbital, the more likely it is it's an insulator, and then vice versa. Did we get that?
Sure.
Kind of. Yeah.
What determines if the electron will go up and fall back down?
Well, it's usually energy being passed from something else, yeah. But also what the components of this metal is. Okay, so silicon can do this, but if you've got extra electrons like phosphorus, they might be more likely to jump because they're unpaired. Or something, it depends on the impurities you put into your silicon derivatives. Okay, so this is what that says. And this is called the band theory, okay? So I'm going to let you write what you want. Yeah. Just to do with energy levels. The bond orders are if something will exist or not. This has to do with if it exists, can it conduct? Yeah.
So is this just for
Semiconductors.
Oh, just for
Yeah.
semiconductors.
I didn't mention, it's called a band because there's like tons and tons and tons of these same energy levels repeating themselves. So it essentially forms like a band of bonding orbitals and a band of anti-bonding orbitals, and there's this gap in between it because there's millions of these things lined up together. So write down what you want. The most important thing is probably the conclusion, because most of the time when you think molecular solids, you don't think conduction. You just don't. But some of our network covalent solids can conduct. The reason why is either because they're like graphite with the whole empty p or unhybridized p orbital, and they've got that space for electrons to move about, or because it's a semiconductor, and there's a small enough gap between the bonding and anti-bonding areas that the electrons can move. So really, only two cases you can have a conducting molecular solid. do phase diagrams really fast, guys. It's all. All right, thumbs up. You guys ready? I'll give you another second. You're going to sketch a heat curve. What does a heat curve look like?
It's like
It's not a curve, right?
Yeah.
It's not a curve, Nick.
It's that one.
It's a stair step, like this.
See where you're at.
Okay, sketch me a heat curve. Big, because I'm going to tell you what goes along each of the plateaus and so forth. Can I go past this?
Yeah.
Okay. Alright, so I just skipped ahead a little bit because I just had some little stuff, I can do that tomorrow. So a heat curve looks like this. La la. Ice. Water. Water. Water and steam. Steam. Okay, so I'm just going to review with you what's happening at each of these transitions. I'll scroll. Oh, it's like this, and then I'll tell you at the top.
Okay, thank you now. We're good.
So you've got energy added across the x-axis, and then temperature on the y-axis. This is different than a phase diagram, which has pressure and temperature on its axes. So we're going to go through just the specifics of both of these, but not too long, because I want you guys to start to refer cues in class. All right, temperature and energy added. Okay, so over time, you can cause phase changes to occur because you're adding energy, but energy and heat are not the same. Well, energy, temperature, and heat are all not the same. It all deals with kinetic energy. So if something has a lot of kinetic energy, tons and tons of kinetic energy, what phase of matter is it most likely going to be in? Gas, because the kinetic energy is so large, they've actually overcome their IMFs for each other, and they've separated into the two gaseous molecules. But if you have really low kinetic energy, you slow them down, they start to intermingle, and they start to have their IMFs come back into action, and they turn to liquid or solid phase. What has not happened at any point in time during this phase change? Okay, exactly. During only phase change, temperature doesn't move. During the strict phase change time. But what about bonds? They never change. They're still, and simply, it's just still water. You don't change the bonds, period. You change the IMS, or you overcome IMFs, or so forth, okay? So, along each of those, and those are labeled, I'm sorry, did you see where they are labeled? 1 is the first slant, 2, 3, 4, 5. I'm going to talk to you about each of those, and you can diagram or write what you need to. I'm just going to highlight the important parts. So, under 1, we've got ice, and we're starting out way down here at a negative temperature, and we know eventually when we get to 0 degrees, we've added enough energy, we've hit 0 degrees Celsius, it's going to start to melt. But why? Okay, so the first phase, the slant, the diagonal here, you got energy added. So the energy added increases the kinetic energy. Increasing the kinetic energy is directly proportional to increasing in temperature. So remember that whole kinetic molecular theory, proportionality between temperature and kinetic energy. That little fish means proportional. Okay. So energy is increasing in the solid. Generally, it's going to increase the vibrations. Those vibrations take on, are essentially just kinetic energy because it's energy of motion. The temperature increases because kinetic energy is increasing, and the temperatures happen at the same time. Until the point of no return, when you actually start to phase change. The kinetic energy is so high, the solid can't stay in its solid phase anymore, and it starts to transition to liquid. It doesn't immediately go to liquid phase, though. The molecules just become energetic. They break loose from their specific lattice structure. And when they start to break loose, some of them are going to break loose before others. So that's why you have this in between where it's starting to melt, where some of it's still solid, but some of it's starting to turn to liquid, basically because your IMFs are being disrupted. So they change the molecules become so energetic they break loose. The energy added disrupts the crystalline structure and the IMFs. I'm underlining and writing down the important stuff here. So the energy added is not going towards making more kinetic energy or going towards increasing temperature. All the energy that's being added is simply going to moving the molecules away from each other to overcome IMFs. That's why there's a plateau. That's why there's no change in temperature during phase change, because there literally is no temperature change when all the energy that's being put forth is used to just pull apart two molecules. The equivalent of the energy used to overcome those IMFs between those two phases of matter is called the enthalpy of fusion. It's that energy that's put forth to overcome the IMFs between the solid and liquid phase. Yeah.
Are we going to be given the numbers that we need for like each part or whatever?
You mean like the delta H for it or something? Yeah. So like the delta H for water fusion is 6.01 kilojoules. Or you would like calculate it from information. Okay, so for curve 1, temperature is changing. What equation comes to mind from thermochem? Q is equal to MCAT, because that's temperature changing. Okay, temperature is increasing, temperature is changing. Q of the system is equal to what of the surroundings? Negative Q, right? So this would mean the temperature, the energy of the surroundings is losing, while the energy of the system is gaining. Temperature increases. This one, there is no delta T. So we've got Q is equal to either M in terms of moles times the delta H of fusion, given as kilojoules per mole, or they can also publish them. It's like 334 joules per gram of water. It's published different ways. It depends on what's given to you as to what variables you use. Okay, so then again, we've got phase, or we've got liquid phase. Liquid phase, you'll increase the energy added, you'll increase the kinetic energy of the molecules. They overcome their small amount of IMFs that are still remaining. For water, what IMF is it? Hydrogen bonding. Okay, so it's going to continue to overcome the hydrogen bonding between the liquid molecules. As that occurs, they become really energetic and their motion increases. The energy of the kinetic energy, which is the energy of motion increasing, causes the temperature to rise. So there we have delta T, and there we would also have Q is equal to MCAT if we had to calculate for that. Again, temperatures flat lines because the energy that's added at phase change is not going towards increasing kinetic energy. It's overcoming the IMFs between them fully, and at that point we call that delta H vap, because it's allowing for vaporization to occur as the potential energy of the molecules increase. Potential energy because they're farther away from each other. So no delta T, so we're using that equation again. And then you guys know the final part. So pretty much the entire time we only had changes to motion, kinetic energy, potential energy, temperature, IMFs. Never changes to the structure of the chemicals. Never bond breakage, never bond formation. Never change the chemical structure. It's literally still the same thing, just change the way it looks, the phase of it. So no chemical changes, only physical changes. All right, let's do phase diagram. What does the phase diagram look like? Nice. That was a heat curve. We just did heat curves, so it's like a Y. It's like a Y. It's a butt. I love it. Okay. We're calling a butt from now on. Oh, here's ooh, ah, look. Ooh, ah, ooh, ah, ooh. Okay, thank you. All right, so there's our phase diagram. It just looks
Don't get whether it's gas.
Oh my god!
that makes me laugh sketch yourself one for water. The only thing that's different between water and pretty much any other thing, you know, water is weird. Water has a lower density as a solid. Water is polar. Water is a universal solvent. Water, high melts, boiling point. Water is amazing, okay? Water also has a negative slope between the solid and liquid phase on the phase diagram. One of very, 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 very few. Most things have a positive slope. So if you're trying to read a phase diagram, I tried to give you an example as to where we were. So why are we here at this 1 atmosphere pressure, which is AKA, when I say normal pressure, normal conditions, normal whatever, we call normal 1 atmosphere, which is where we normally exist, right at 1 atmosphere pressure. Mount Everest is up real high. So here's me, top of Mount Everest, once or twice, there we go. And there's you guys. Maybe Kim, is I'm here? Okay. So I'm up here, lower atmospheric pressure, because there's less stuff pushing on top of me from all the atmospheric layers. You guys have a lot of atmospheric layers between us, so it's all pushing down on you, crushing you. Okay, so that's going to have more pressure.
That was so aggressive.
That's, I mean, you guys remember Grace's all day story. That's all I have to say. Okay. So I'll never forget this. Okay, so then you can look at the transitions between the phases of matter from solid to liquid. That equilibrium that exists is called the physical equilibrium. Okay, so this whole line here, this line here, and this line here, they're all physical equilibrium. So you can actually do an equilibrium problem with a phase change, because you're going to have X amount of moles of liquid to X amount of moles of gas, or vice versa, solid to liquid, or something like that. But don't forget, in equilibrium, what states of matter do you always exclude? Solids and liquids. So the physical equilibrium here we're probably dealing with is Kp, so the pressure ones, because that's the only one that's going to be really related or able to be incorporated in the icebox period. Okay, so these are all called physical equilibriums. At higher pressures, water melts at higher pressures, water melts at lower, higher temperatures. Melts. It's actually lower because it's a difference, and it's pulling it between the solid and liquid. So at higher pressures, here for example, water melts at, I don't know, -2 degrees, whereas at normal pressure, so a lower pressure, it melts at a higher temperature. Normally, you increase the pressure, you're increasing the temperature at which it melts or changes to gas or something. Water is the only one that goes opposite direction. This phase change is going from solid to gas. That's what? Sublimation, melting, vaporization. What's the opposite of sublimation? Deposition. Freezing, and then gas to liquid. Condensation. Okay. I'm not going to define all the different points of the phase diagram. I think we're okay with that. The only thing I do want to make sure we know it's a closed system. Closed system means nothing escapes. So if something escaped, we would have problems, and we'd have different temperatures at which things melt or boil, or pressures at which those phase changes occur. So it has to be a closed system. That's all I'm going to write for that. I'll let you guys read the other stuff. This critical temperature, critical pressure, critical point, and triple point. Look at that in SMI thing. It's like the last 2 pages. I hate that I've talked to you the whole time. So I'll show you a video at the end. It's been a day, guys. Okay. It's been real. No. He probably just didn't give it to me.
Oh, he had 3